Hello everyone, my name is Mohammad Afifuddin. In this video, we will see another problem based on design of doubly reinforced beam. So here is the problem statement. A beam 250 mm by 550 mm effective is subjected to a factored bending moment of 300 kN. Determine the area of steel required in tension and compression zone. Use M20 concrete and Fe250 steel. Assume D dash is equal to 50 mm. So here is the given data. B is equal to 250 mm. Small d, that is effective depth, is 550 mm. Cover is given as 50 mm. And factored bending moment is given as 300 kN. As M20 grade of concrete is given, therefore FCK is equal to 20 Newton per mm square. Fe250 grade of steel is given, that means mild steel is given, and therefore Fy is equal to 250 Newton per mm square. So this is the given data of the problem, and this problem we are going to solve by two methods. Okay, two different methods, and you can use any method in your examinations. Okay, so here is the first method. First step is to find out the D dash by D ratio. Okay, and D dash by D ratio is 50 by 550, that is equal to 0.09. Okay, so we will take it 0.1. And for Fe250 grade of steel, here is the table. You can see that for 250 grade of steel, the value for FSC is same, that is 217 Newton per mm square. Okay, so here FSC value is 217 Newton per mm square. Now our second step is to find out the limiting moment of resistance, that is MU limit. And as Fe250 grade of steel is given, therefore XU max is equal to 0.53 into D. So 0.53 into 550, which is equal to 291.5 mm. Now the limiting moment of resistance MU limit is equal to 0.36 FCK into B into XU max in bracket D minus 0.42 into XU max. So after putting all the value, we will get MU limit is equal to 224.3 into 10 raised to 6 Newton mm. Now our third step to find out the additional moment of resistance, that is MU2, and this moment of resistance is to be resisted by the additional reinforcement provided in compression zone as well as additional area of steel in tension zone, that is AST2. Okay, so MU2 is equal to MU minus MU limit. MU is 300 kilonewton meter, MU limit is 224.3 kilonewton meter. So 300 minus 224.3, which is equal to 75.65 kilonewton meter, or 75.65 into 10 raised to 6 Newton mm. Now we will find out area of steel 1, that is AST1. We know the formula, MU limit upon 0.87 into Fy into D minus 0.42 XU max, which will give us the value of AST1, which is equal to 2412.4 mm square. Similarly, AST2 is equal to MU2 upon 0.87 Fy into D minus D dash, and which is equal to 695 mm square. Okay, now here we know the value of AST1, we got the value of AST2, therefore total area of steel, that is to AST, is equal to AST1 plus AST2, and which is equal to 3108.1 mm square. Here we will assume 25 mm diameter bars, therefore number of bars required are total area of steel upon area of 1 bar. Okay, so here we require 6.3 number of bars, therefore we will provide 7 bars of 25 mm as tension steel. Okay, now our next step and final step is to find out the area of compression steel, that is ASC, and ASC is given by MU2 upon FSC into D minus D dash. FSC we have calculated, that is 217 Newton per mm square. MU2 is 75.65 into 10 raised to 6 Newton mm. Small d, that is effective depth, is 550 mm, and the cover is given as 50 mm. Therefore area of steel in compression which is equal to 692.3 mm square. Now we will assume 16 mm diameter bars. Therefore, number of bars required are 692.3 upon pi by 4 into 16 square, which gives us 3.4 number of bars required. As practically it is not possible to provide 3.4 number of bars, therefore we will provide 4 numbers of bars of 16 mm diameter as compression steel. Okay, so here we have completed one method. Now we will see our another method to solve this problem. The given data is same here. Okay, so first step will be to find the XUmax value. XUmax is equal to 0.53 into D. So after putting the value, we can get the value of XUmax. Then we will find out MU limit, and for Fe250 grade of steel, MU limit value is 0.149 into FCK into BD square. Okay, now after putting all the value in the formula, we will get MU limit is equal to 225.36 into 10⁶ Newton mm. Okay, now we will find out the percentage of steel, that is PT limit. So for M20 grade of concrete and Fe250 steel, here is the value in table. We can get the value of PT limit, which is equal to 1.76%. Okay, so from the formula of PT limit is equal to 100 into AST1 upon B into D. We can find out the value of AST1. So after putting all the value, here we have calculated AST1 is equal to 2420 mm square. Now similarly, we will find out the additional bending moment, that is MU2, which is equal to MU minus MU limit. After putting the value, MU is equal to 300 kN meter, MU limit is equal to 225.36 kN meter. Therefore, MU2 is equal to 74.64 kN meter. Now we will find out the ratio of D dash by D, and which is equal to 0.09, which is or nearly equal to 0.1. So for Fe250 grade of steel, FSC value is equal to 217 Newton per mm square. Okay, now FCC is equal to 0.45 into FCK. So 0.45 into grade of concrete is 20. So 0.45 into 20 is 9 Newton per mm square. Now our next step is to find out the area of compression steel, that is ASC. We know the formula. Here is the formula, and after putting all the value, we will get ASC is equal to 717.69 mm square. Now we will assume 16 mm diameter bars. Therefore, number of bars required are 3.57, and we will provide 4 bars of 16 mm diameter as compression steel. Now next step is to find out the AST2. So from the equation ASC into FSC minus FCC, which is equal to AST2 into 0.87 Fy, we can find out the value of AST2. So here after putting all the value, AST2 is equal to 686.34 mm square. Now we will find out total area of tension steel. We know the value of AST1, we know the value for AST2. So after adding both the values, the total area of tension steel is 3106.34 mm square. Okay, now here we will assume 25 mm diameter bar. Therefore, number of bar required are 6.32. So we will provide 7 bars of 25 mm diameter as tension steel. Okay, so these are the two methods. You can use any method, and the answer will be, and the result will be the same. Okay, thank you.